Good morning, everyone. I have to say that I'm delighted to be here. I want to thank the organizers for the opportunity to talk to you today. I also have to say that with any of us speaking here today, the challenge is to represent many things going on in the field in only a few moments. So I'm going to talk about in situ and operando methods because I believe they're so critical towards the understanding of these highly, highly complex systems. But I also want to say that there are many people in the audience, many people who are listening, our moderator, who are profound pioneers and experts in this field. So I certainly want to acknowledge all the people who have made many of these things possible. I want to start with just a few definitions. When I first started working in batteries in the medical field, the best tool we had was destructive analysis. Test a battery for a while, take it apart, take out the pieces, and hope you can figure out what happened. And these days, things have changed dramatically in that in situ and operando methods have become approachable by folks working in the battery community. However, I did a quick search in Web of Science, just using simple terms, battery and in situ, battery and operando. And we can see that while, 20 years ago or so, there certainly were people working in that area, it's really been about the past 10 years or so where the number of publications, including in situ and operando data, has just grown by order of magnitude. So it's really been a huge improvement. And I think the biggest thing is that using operando methods, you get insight into kinetics, which is, of course, hugely important when we're talking about electrochemistry. So I want to acknowledge Department of Energy, Craig Henderson, our program officer. I really think that the Energy Frontier Research Center has been a tremendous vehicle for bringing together disparate backgrounds of people who are experts in characterization, synthesis, electrochemistry, multiple types of theorists, continuum modelers, and DFT. And this has allowed significant advances in understanding by bringing together these communities with specific goals that they're trying to accomplish. And what we were really interested in was transport, and certainly transport over multiple length scales. What we find in very complex battery systems is that the atomic/molecular level, the crystallite, the particle, the aggregate, the electrode, all matter. They can all contribute to localized resistance that then impacts how the system functions. It impacts the loaded voltage relative to the open circuit voltage. And ultimately, that determines the amount of energy that we can realize from the battery. Not much how much is in there, but how much we can actually realize. And by using multiple probes over various length scales, that's the path towards understanding what's really happening at these multiple length scales and then how those relate to the system. As we heard about this morning from Stan, conceptually, there are two major types of battery materials. One are insertion-type materials where there's minimal structural change. There are also conversion materials where the material is turning into something new. The intrigue there is high capacity. They have challenges, but they certainly need to be pursued because there you have the opportunity for multiple electron transfer per center. So I'm going to give some examples from magnetite. Several things are appealing about magnetite. Cheap, readily available, non-toxic. If magnetite can be fully accessed, there's 8 electron transfers per formula unit. And as you can see on the charts below, the interest in magnetite over the past several years in terms of the battery field has also been increasing. So to begin with, we need to start with the atomic molecular level to understand what really are the reactions of magnetite. And this is some lovely TEM work in collaboration with Feng Wang at Brookhaven National Lab, demonstrating that we start with Fe3O4. There's initially a lithium insertion reaction. Then we move to FeO, finally to iron metal, lithium oxide. And what's important about this work is that the oxygen anion framework is largely retained. So it's possible that the retention of that oxygen anion framework is part of the reason that these systems are reversible at all. Moving now towards in situ work, so now TEM has advanced to the point where lithiation and other types of reactivity can be monitored at an atomic level while happening in a transmission electron microscope. So this then reveals specific ionic transport pathways in the material because high-level resolution is possible while it's time resolved. So this is an example of instrumentation advance that has happened in the past several years that really allows new insights to be gained at the material level. Let's move up the length scale a little bit. So magnetite is an inverse spinel, so fairly densely packed structure. By careful synthesis using co-precipitation methods, Ken Takeuchi developed methods where we can prepare these materials without surface treatment or without capping agents. And we find that the electrochemistry is in fact dependent on the crystallite size. And not surprisingly, the higher the rate, a 1 hour rate, we see a bigger difference between the crystallite sizes, albeit both of these crystallites, relatively speaking, are small. You know, we're talking about 8 nanometer, 28 nanometer, but yet we see a difference in the electrochemistry. When we move on to the electrode level, what we find is that these finely divided materials do aggregate in the electrode. So the question is, what's dominating the transport? Is it the crystallite size or is it the aggregate? Some very nice continuum modeling done in conjunction with Alan West at Columbia University, who took on the challenge of looking at transport through the crystal using a core shell type model and an agglomerate of these tiny crystals. And in fact, it turns out that both matter. In order to develop a model that in fact represents fully the voltage profiles of these systems, both the crystal model and the agglomerate model must be combined into a true multi-scale model. And he, in fact, can predict, depending upon what rate you're using, what crystal size you need. And the goal ultimately is to minimize agglomeration because it creates a second limitation to transport within the electrode. One of the operando systems or methodologies that I appreciate, this is something that we used extensively in medical batteries, is looking at heat dissipation of batteries. Not only under open circuit voltage, but while they're functioning, because it provides insight into parasitic reactions. And often, long life batteries are not limited by their active material content, but they're in fact limited by the parasitic reactions that are taking place inside the battery. And what we find are two interesting things. If we look carefully, we know the theoretical reaction should generate 8 electron transfers. We can calculate the amount of heat we should produce, and in fact, we get more than 9 electron transfers, and we get more heat than should be predicted. And if we look at 2 different crystal sizes, 12 nanometer and 29 nanometer, to be honest, unexpectedly, we saw that the parasitic heat is greater for the 29 nanometer. By taking into account polarization and tropic contributions, we can model those, and for the first 2 electrons predict very well how the battery should behave in terms of the heat generation. But it's about 2 electrons where we see deviation, where the total heat is larger than we can account for based on polarization and entropy, thus a parasitic reaction. So I want to turn to X-ray absorption spectroscopy and point out that multiple characterization tools, when brought together, can then lead to profound insight on what's happening in the battery. Operando X-ray absorption can provide us information about the oxidation state through Zanes. And XAS is also not dependent on long-range order, so you don't need highly crystalline materials to gain insight. By using XAFs, we gain information into the coordination environment and structure of the materials. And we can also do mapping, where we find not only where are the active particles, but then we can interrogate the particles and aggregates for their oxidation state on a local level. And this methodology was extraordinarily useful in gaining insight into the calorimetry results. We conducted in situ, actually operando Zanes and XFs for a discharging and charging battery. And we know that if the Faradaic reaction, meaning reduction of the iron centers, is what's happening, then we can predict the average oxidation state of the iron. Every electron transferred should lead to reduction of 1 iron center. And up to about 2 electrons, we get excellent agreement. If you look at the middle chart, the dashed line shows the predicted value, and the dots are our measured values. But at about 2 electrons, we get deviation, where the iron metal oxidation state stops changing. The battery keeps discharging, but the iron oxidation state isn't changing. And after a while, it begins to change again, but the iron oxidation state remains too high relative to theory. And what we're able to establish that location at about 2 electrons is the onset of electrolyte reduction. So that's where something called the surface electrolyte interface begins to form, where instead of reducing the iron centers, we're in fact reducing the electrolyte, forming a film on the surface of the magnetite electrode. And then after we reduce sufficient electrolyte, then the iron reduction continues to form iron metal. And control of that interface is critical to the reversibility of the system. We then probed the size dependence of the calorimetry, investigating both 12 nanometer and 29 nanometer magnetite, and mapping it using X-ray fluorescence, and then conducting a local probe of the iron oxidation state, both in the center and the periphery of the aggregates. And what we found was quite interesting. With the small crystallite materials, there's a difference during the reduction process, the operando process, of the oxidation state of the iron at the surface of the aggregate versus the center of the aggregate. But for the 29 nanometer material, there's much less difference, meaning that those agglomerates are porous enough to discharge fairly uniformly, which gives us insight into why the parasitic heat is higher for the larger material. So now I'm going to move up length scales again and contemplate tracking lithium and the lithiation through thick electrodes. Ultimately, thick electrodes, if they can be efficiently utilized, will contribute to high energy density batteries, as well as possibly scalable batteries. We use a tool called the energy dispersive X-ray diffraction. So this is a synchrotron method where we use a 20 micron beam, then move the battery through various locations in the electrode so we can map the progress of the reaction through the thickness, as well as different areas in the XY direction to see how the reaction is progressing. And in this case, one can see that the full reduction of iron metal is shown in the middle here. And in this case, the full reduction does not penetrate the entire electrode. We go on to do an operando experiment. So we're discharging this battery and measuring the ED-XRD through the cross-section of the electrode continually. And we can then find out that this reaction is in fact limited by lithium-ion access. The reaction that goes to completion is at the electrolyte interface. So this clearly tells us that kinetically, in order to utilize this electrode, we need to redesign the electrode to be able to capture more than 30% of the full realization of iron. So here's an example of a three-dimensional porous electrode. Again, probed via ED-XRD, and if we conceptually envision that we need ion transport throughout the electrode, then this is an example of getting full utilization and formation of iron metal throughout the electrode. And if we compare the capacity that we can obtain in a very thick 500 micron thick electrode that's densely packed versus a 3D electrode, we can see that there's really a difference in utilization of the active material. The concept of non-planar and 3D electrodes is an important one. The majority of batteries today, certainly lithium-ion batteries, are made using metal current collectors and actually quite thin electrodes. And the reason is because ion transport is the limitation. But when contemplating large-scale batteries, then there ends up being a fair amount of inert material in terms of many layers of metal, many layers of separator. Further, if you want to pair a cathode with a high-capacity anode, silicon, tin containing, even lithium metal, you need a very high-capacity anode. And if you simply take this 2D architecture and make it thick, you won't be able to utilize that active material. So this is an example, a project that we did with Lyndon Archer at Cornell, looking at non-planar electrodes that have very high areal loading in terms of being able to achieve effective utilization. We tracked these areal loadings by XAS again, and found that the utilization of very high loading and moderate loading is very similar as long as we have these three-dimensional electrodes that have high ion access as well as high electrical connection within the electrode itself. So now I want to turn to the idea of multifunctional material design. Most electrodes are fabricated by something called a composite. So with the active material, we have typically a conductive additive or coating, usually carbon, then a polymeric binder, basically to take all of those powders and stick them together and have them adhere to the metal foils. So the notion that we had was if we have a material that can spontaneously form a conductive layer upon each particle through a reduction displacement reaction, this would be a way to achieve an intimate network of electrical connection within this electrode that the material could generate itself. The example I want to show you is silver vanadium phosphorus oxide. Phosphates typically are not conductive. They're pretty resistive. The idea was by including a silver cation, reduction of that silver cation should be able to, silver metal should overcome some of that resistance. This material is also important because the solubility we were able to demonstrate is much less than the oxide. Silver vanadium oxide is an important commercial battery. It's used for implantable cardiac defibrillators. And in fact, vanadium dissolution is one of the life-limiting features of that active material. And by going to the phosphate, we can minimize dissolution. We can demonstrate this by XAS and verify it by comparative pulse data after a very long discharge. So the phosphate material does, in fact, form silver metal. We can track this by SEM and XRD. There's profound change in conductivity on initiation of reduction. We can do this on a single particle. Take an individual particle, you view the active cell through an optical microscope, the reduction of the particle takes place, and then by using a nanoprobe measuring the local conductivity of a partially discharged section as well as a pristine section, we again see many orders of magnitude change in conductivity through partial reduction. EDXRD has been extremely useful here. We can map where the silver forms. We can map the silver network. Silver is a heavy atom, and we readily see this through diffraction. And what we find is that the formation and the homogeneity of the silver network is rate dependent. If you set up the network first at low rate, you get very uniform formation of silver metal. If you try to discharge it really fast initially, the silver metal forms like highways through the cathode, and it's not as uniformly distributed. That's kind of illustrated here. Slower is more uniform. The other thing that EDXRD allowed us to probe was the impact of binders. You know, binders have been viewed as not really mattering. They're there, but they don't matter too much. And it turns out that binders if they're insulative, they negatively contribute to the function of the battery. If we have a material that can generate its own conductive network and we have a binder present, the behavior is even worse. Of course, adding carbon overcomes this, but this has led to, for us, a field of inquiry looking at conductive binders to minimize the impact on transport of electrons throughout the electrode. I'll move quickly through a new material and then end with some views of some future initiatives I think that are important to the battery community as well as society. Lithium vanadium oxide, high-capacity material with potential of over 300 milliamp hours per gram. It has multiple phases that form, alpha, lithium-rich, and then beta phase. If we track this material using a thin electrode and angular dependent X-ray diffraction, we can track these phases. It tells us what's happening. It doesn't tell us where it's happening. If the electrode is thin enough, a lovely continuum model can be developed that just depends on the size of the particle itself. If we go to a thick electrode, now that's where the transport through the electrode becomes important. And by combining theory modeling with experiment, where we can actually monitor the phase fractions forming as a function of time to get spatio-temporal resolution and combining that with a continuum model, we now have the ability to predict not only what's happening, but where. So this is my view of the future, a little bit. I agree with Larry's comments this morning that batteries are going to be a dominant technology moving forward. Critically important for electric vehicles, critically important for our future vision of what the electric grid needs to look like with renewables. But the challenge that we're all going to face is what's going to happen with all of these batteries after they eventually reach their end of service. So one of the things we've been thinking about is it possible to regenerate batteries? So not just recycle them in the sense of chopping them up, leaching out elements, but can we regenerate them? And so one set of experiments that we did was developing fibrous materials. In this case, the active material is vanadium oxide, combining it with a carbon fiber for conductivity. So this is a self-standing, self-supporting porous electrode with no binder present. We cycle, then remove the electrode from the battery, simply rinse it off, put it in an oven, bake it at 200 degrees for a couple hours, put it back in the battery. And you can see that the control, where we just rebuilt the battery, doesn't seem the level of improvement that we see with this regeneration process. And in fact, we can regenerate these electrodes over and over. And again, we've demonstrated this with vanadium. We've demonstrated this with manganese oxide. So in fact, it works. We've done extensive characterization before and after regeneration to understand the phases that are formed, why this works. We've done mapping, we've done EDXRD, we've done Operando XAS. And in the case of the manganese materials that we've looked at, they in fact restore the original structure. In the case of this vanadium material, interestingly enough, the phase that ends up contributing to lower capacity as it originally cycles is transformed under these conditions into something new. We start out with V205 and phases of that and end up with LiV308, which is one of the materials that I talked to you about. So in fact, we are able to demonstrate regeneration. So I'll quickly summarize by saying that all length scales matter. And monitoring things using multiple methods to gain insight over multiple length scales and then tie them to the functional battery is critically important and provides insight not only into design of materials, but design of the subsystems that govern the transport and thus the electrochemistry of the battery. And I think transport and kinetics are critical in efficient utilization and still an area that will benefit from fundamental inquiry. I want to thank and acknowledge the Takeuchi Research Group, my collaborators, Ken Takeuchi and Amy Marshallock, our EFRC team that works so well together, bringing together these diverse disciplines. And most importantly, perhaps I want to acknowledge and thank the funding agencies that have allowed us to pursue the directions that we've pursued. And thank you very much for your attention.
We have time for a few questions.
Esther, what is your wish list? If you really want to pursue operando studies, what things would you like to know in the future that you can't quite get to now?
I think bridging length scales is really critical, that often each method gives us insight into one length scale, and then we need to tie those things together. But I do think that the operando methods are critical because those are the ones that provide insight into kinetics and transport properties. And I will emphasize again that I think that bringing together characterization folks, electrochemists, theorists, modelers are how we take information and turn that information into true insight into what's governing the transport properties in these complex systems.
I'll take priority here and add a little comment to that and maybe slamming NSF a little bit. But we need access to these facilities, and unfortunately NSF is walking away from supporting large user facilities. Chess, for example. What's that? No, I mean, the reality is that right now, all of this synchrotron work, it's almost like a little club. Fortunately, I'm part of that club, but I can see, where access to that has to be critically important. Deborah.
So many things to discuss, but I think your last point with respect to regeneration rather than recycling is critical. Nature just published a study that the more cobalt you take out of a lithium battery, the less economically viable it is to recycle. The amount of lithium in there is not shall we say, a market driver. And you know how I love thinking about wiring in 3D. So it's important that you're finding that's an effective way to, if you will, reuse.
Thanks, Deborah. I agree. I think that that's going to be an area of inquiry that really demands a lot of fundamental science in terms of how can we not only extend the life, but re-envision and reuse these systems. It's not a trivial question. And that's where understanding and controlling parasitic reactions becomes so critically important. They're difficult to study. They're difficult to measure because ultimately batteries that work well have these reactions taking place at a very low level, but it can be done. Thank you.
On that note also, where do we see the future of 3D batteries?
I think
I mean, a lot of people talk about it, and very few examples of that.
So since I'm the person who first, thought of it from ONR funding, it seems to me microbatteries is the easy application space, and so you've seen
power fly.
Exactly. So that's why we've brought that sort of non-periodic, spongy scaffolding up to zinc. And to me, that allows us to rethink the all-solid state, high transport, interpenetrating co-continuity with not based on lithium, but based on zinc.
And I think, Deborah, what you said earlier is right. You have to maintain electrical contact, but allow those ions to get in there. And thus, these three-dimensional architectures are important for enabling high energy content electrodes.
It's the Rollison corollary to Moore's law. We have to control too many per second functions, whereas in computation you're only worried about the mobility of the electron or the hole. We've got multiple length scale transport. We've got multiple phase transport in the electrode kinetics. So, we're looking at a 1/2 to the n where we're doing 3 to 5 things that have to be done right in the battery, and even in energy conversion.
And quickly.
Right.
I think we're out of time, but what the hell, dude? Go ahead.
I'm Mark Jones from Dow Chemical, and I'm on the CSR, and I guess I want to maybe open an illuminating statement. I lived through catalysis where many people were saying we need to invest in operando, we need to invest in very first principles studies. And over my 30 years, I have not seen one example where the first principle studies actually produced a better catalyst. And certainly in industrial research, high throughput methods, combinatorial methods have been what has won the day in spades. So I guess that if I would offer the caution that I think you want to also be open to other methods of discovery that don't necessarily have to underpin on the foundation of theory and operando.
Thank you for that comment, because one of the challenges with first principles modeling is that they don't often take into account kinetics. And kinetics is what really determines functionality. I can take any element in the periodic table and I can tell you theoretically what the energy content of that element is. But how it's going to behave in a working system, I think, is really where kinetics and transport are absolutely critical. And I think that same statement can be made relevant to catalysis. So notice the examples that I gave were continuum modeling, where we are using Butler-Vollmer kinetics, really thinking about diffusion and then trying to accurately predict actual voltage profiles of a working system. And I can tell you, working at the continuum modeling level, we have examples where modeling has led us, and where us meaning the experimentalists, me, and examples where the experimentalists have said, hey, your model doesn't work. So I think it's that interaction that really is a differentiating feature. But if you don't include kinetics and transport, then it's very difficult to say that you have a prediction. So thank you for your comment.
We're going to have to stop right here, folks, even though I would love to continue the discussion, but it's a good seat, for the break.